All right, we're going to start with Chapter 3. I apologize for the difficulties we were having online. Hopefully this will come through more clearly for you. Chapter 3 is going to be discussing radiation characteristics. In the last chapter, we talked about radiation basics. We talked about the technical factors that can be on a control panel, such as kilovoltage, milliamperage, time. Usually you really only have control of time, but we're going to talk about kVp, MA, and time, as well as distance and what effect that has on the image that we create. This control panel image is found in your book on page 25, and it looks very much like ours in clinic. We do have the option to choose 60 or 70 kVp, and we'll talk about what effect that will have on the image that we create. X-ray beam quality is controlled by all of these things listed: voltage and kilovoltage, kilovoltage peak, density, and kVp. We're going to talk about the effect kVp has on density, the effect kVp has on contrast, and exposure time and kV. So the kilovoltage peak, you're going to hear us talk a lot about kVp, and that's what that's referring to. It controls the quality of the X-ray beam, which measures the speed at which the electrons are going to travel. So it's the peak voltage of the current. Again, kVp is going to be associated with quality. I would definitely remember that. It's used to describe the mean energy or penetrating ability of that X-ray beam. Quality is controlled by kVp. And remember talking about wavelength in the last chapter when we were talking about the electromagnetic spectrum and how the more penetrable rays have a shorter wavelength and a higher frequency. Kilovoltage controls that. So we're kind of applying this to the information that you learned in the last chapter. You'll hear it called kVp typically, but voltage, if you're familiar with electrical terms, voltage is that electrical force that will cause the electrons to move from that negative cathode where they build up to the positive anode. There's a typo on this, so that should say anode there. If voltage is increased, that speed of those electrons will also increase, and the electrons will strike the anode target with greater force. So the higher the kVp, the more driving force behind those electrons. Typically, voltage is measured either in volts or kilovolts, and in dentistry we use kilovolts, which is equal to 1,000 volts. Dental radiography typically requires the use of 60 to 100. Now that's talking about all types of radiography, be it intraoral or extraoral. Intraoral images like bite wings and the full mouth set of x-rays that you guys will take, anything that's inside the mouth is will be in the 60 to 70 kilovolt range, and even on our panoramic machine we don't go any higher than, I believe the max that can go is 82 or 83 kilovolts. The maximum or peak voltage usually refers to that peak voltage of alternating current. So when you see the current go up and down, it's at those peaks of those waves where the maximum peak is located. Oftentimes you'll hear the X-ray beam referred to as polychromatic. That just means that it's produced as a result of varying kilovoltage in the tube current. And quality, again, is the wavelength and energy of the X-ray beam controlled by the kVp. Now density. Density is the overall darkness of an image, and we learned the different interactions that X-rays have with matter in Chapter 2. And if an electron or an X-ray comes into a cell and has no effect and goes right straight through, there's no interaction, that creates complete darkness or density on an image. Now it can be varying degrees depending on what that X-ray hits as it goes through. If it's somewhat absorbed, it will be more in the gray range. If it's completely absorbed, like by an amalgam, it's going to be completely white. It won't let any of the X-ray through to create any degree of darkness or density on the image. So when KVP is increased, the image will appear darker because it gives those electrons or X-rays more power, more penetrating power. So KVP does slightly increase density, and it will make the image appear darker. So if you turn down KVP, the image will have the opposite effect and appear lighter. So KVP does have that direct relationship with density, but it is not the controlling factor of density. If we want to control density, we are not going to change our KVP. We would change our time or our MA. KVP is used to control contrast. Contrast and KVP, I wish I were standing in front of you, because students tell me when they go to boards they picture me with one thumb up and one thumb down. For KVP, always picture me with a thumb up and a thumb down. If I increase KVP, I'm going to decrease contrast. It has an inverse relationship, and the opposite is also true. If I decrease KVP, I'm going to have higher contrast. What does that mean? Contrast is how sharply dark and light areas are differentiated from each other on an image. So it's the overall lightness and darkness of the image. If an image has high contrast, it has lots of black and white. If it has low contrast, I picture a long scale of grays to black. So high contrast is black and white. Low contrast is lots of grays. So again, remember, KVP is the controlling factor for contrast. MA and time are not going to be changed at all for contrast, and they have no effect on contrast. Contrast is strictly a KVP issue, and it is that inverse relationship. Let's say that you're working for a general practitioner who is looking for decay. They are going to want high contrast because they want to see that definite decay, black and white. Whereas a periodontal or a periodontist wants to see more shades of gray because they're looking for possibly a periapical lesion, abscesses, things like that, that the differing shades of gray are helpful for diagnosis. Here's an example of a high contrast, low KVP scale. You can see there aren't very many shades of gray, and it's pretty black and white. Whereas high KVP, low contrast, has a much longer scale with lots of grays in between. Exposure time and KVP. So what happens if I adjust my time? What happens as far as KVP goes? Well, the longer my machine has to produce X-rays, the more X-rays are going to be produced. So if KVP is increased, time must be adjusted to maintain density. So that's something to think about. If I'm going to increase my KVP and I want things to stay the same, I'm going to have to change my time, because again, that's the only thing we have control over. Time in the X-ray machine is measured in impulses per second, and most often you're going to see them put MA and time together, so it'll read mass, and we'll talk about that when we talk about MA here in just a minute. So X-ray beam quantity now. When we were talking about KVP, we were not talking about quantity, we were talking about quality. Now we're going to talk about quantity. What is going to control the number of X-rays produced. And that is going to be amperage, which is going to be stated in milliamperage in the X-ray machine, possibly milliampere seconds, which is that mass I was speaking of. We're going to talk about how density and MA relate, exposure time and MA relate, and again, the quantity of the X-ray beam is the number of X-rays produced in that dental X-ray unit. So amperage is going to determine the number of electrons passing through the cathode filament. So remember your C- to an A+. The cathode is the negative side of that X-ray tube, and it has that tiny itty-bitty filament that requires the low volt to heat up enough to create electrons all around that coil, and then the kVp is applied, which gives the electrons the power, the driving power or penetrability to go across to that anode target, which is a positive, and that's where X-rays are actually produced. So if I increase the amperage or the MA, I'm going to increase the number of electrons that are created and available to travel from that cathode to the anode. Quantity is also referred to as current. It's the number of electrons created, number of X-rays produced, or current. So all of those things could be associated with amperage. If I increase MA, it has a direct relationship with density. So MA is the controlling factor for density, where kVp is our contrast guy. So if I increase MA, I increase density. If I decrease MA, I decrease density. So that's a direct relationship, whereas kVp in contrast was an indirect. If I increase kVp, I decrease contrast. So remember that. The ampere is that unit of measure that I said that's used to describe the number of electrons or current flowing through that cathode filament. We report that in milliamperes in radiography, so it's 1/1000th of an ampere. And in dental radiography, the MA will range from 7 to 15. Exceeding this amount would produce excessive heat and would probably blow your filament. And if you ever hear of somebody talking about a blown X-ray tube, that's what they're talking about. That little bitty filament that's that tungsten wire over time will break. So that's what they are referring to when they say they have a blown tube. MA and time have an inverse relationship. So, okay, MA and time, if you think about it, if I increase MA, I'm going to produce more electrons. If I give the machine more time to produce, it's going to produce more electrons that can become X-rays. So let's say that I want to be faster in my exposure. Maybe I have a patient that is shaky. Maybe they have Parkinson's disease. Maybe it's a child that can't sit still for me. So I want to decrease my time. And in order to get the same amount of density on my image, if I'm going to decrease time, I need to increase MA to maintain that density. Same thing if I need to decrease MA and I want to maintain density, I've got to increase my time to weigh that out and make it come out the same density as I had in the beginning. So mass, like I said, is the product of MA plus exposure time. So MA plus seconds or time equals mass. If MA is increased, exposure time must be decreased to maintain a constant density. There are 3 exposure factors on dental X-ray units that we've talked about so far. We've got our kVp, contrast, MA, density, and time, also density. If we change any one of those 3 factors, it is going to change the appearance of our image. And remember, most X-ray units will only allow adjustment of exposure time. Like I said on ours, the kVp gives you the option to choose 60 or 70. So if we chose 60, that's going to be lower, so that's going to give me higher contrast. So if you're working on a patient and you're wanting to see more black-white, you would choose 60. If you were more concerned about periodontal issues, you might choose 70 because that's going to give you more gray, a longer scale of grays. So that's kind of how that works. X-ray beam intensity. Okay, my overall intensity is going to be the combination of the quality plus the quantity, and that is going to give me beam intensity. So all of the things listed here, KVP, MA, time, the distance. We're going to talk a little bit about inverse square law and half view layer, but KVP, MA, time, and distance all have an effect on the overall intensity of my X-ray beam. Again, quantity is the number of X-ray photons. Quantity is controlled by MA and time. Quality is the energy of each photon, which is my KVP, or penetrability, and that is what equals our beam intensity. So KVP regulates, and this is on page 27 in your book, KVP regulates the penetrability of the X-ray beam by controlling the speed of the electrons that travel between the cathode and anode. Again, higher KVP means that the beam has more energy, shorter wavelengths, so it's going to increase intensity of that X-ray beam. MA controls the penetrating power of the X-ray beam by controlling the number of electrons produced. So higher MA settings are going to produce an X-ray beam with more energy. It increases the intensity of that X-ray beam. And time, again, is going to affect the number of X-rays produced. So longer exposure time, more X-rays, and again, a more intense X-ray beam. Now, distance is something we haven't talked about. In your book, if you look at page 28, and I think I also have a picture of it here in the PowerPoint, it talks about all the different distances. I want you to think about distance. When they talk about target, they are actually talking about the anode target inside the tube head. They're not talking about, I think we think of target as what we're aiming at. So you might think of it as the tooth that you're trying to image. But in this case, when we're talking about our distances, whenever they say target, remember they're referring to that anode tungsten target inside the tube head. So target to surface distance is from that anode target in the tube to my patient's skin, the outer surface of their face. Okay, and then target to object is the actual anode target to the object that we're trying to image, which would then be the tooth. And then target to receptor is anode target to the actual image receptor, be it film, sensor, PSP plate, whatever you're using to record your image, that is the receptor. So take a look at that picture and familiarize yourself with that, and just remember, target's always inside the tube, surface is the skin, object is the actual tooth, and then the receptor is the film or sensor. So as X-rays travel from their point of origin, and their point of origin is that focal spot on the anode target, they diverge. So X-rays want to spread out. They want to cover a larger surface area. So the intensity of the X-ray beam is reduced as our distance increases. They have a flashlight, for example, in the bottom of page 28. And it shows you how the flashlight's concentrated beam is more intense the closer you are, and as you back that flashlight out, it diverges or spreads out, covers a larger surface area, and its intensity decreases. Same thing with an X-ray. It does the very same thing. So that is where the inverse square law comes in. The intensity of radiation is inversely proportional to the square of the distance from the source of my radiation. So let's say that I'm a radiographer and I am standing only 3 feet from my source of X-ray to my patient. If I back up to 6 feet away, which is where we're supposed to be from that radiation, the exposure of radiation to me is going to be 1/4 as intense to my body as it would have been at 3 feet. So if I double my distance, I decrease my exposure by 1/4. If I'm standing at 6 feet and I move to 3 feet from my beam, I am multiplying it by 4. So it's a squared of the distance. So if you're having or doubling, you're going to square that. And there's a chart in your book on page 29 that talks about that. And there are also some problems that talk about the inverse square law and how to figure that. When you are trying to, let's say you're given a word problem like they give us here on page 29, and it says if the target to receptor distance, so that's to my image receptor, is changed from 8 inches to 16 inches, how does this increase the source to receptor distance? How does that affect the intensity of the beam? So if I am changing my distance, if I'm using a longer PID, then it's going to decrease the intensity that reaches my patient because it's traveling a longer distance, just like that flashlight. If I back that flashlight up, it's going to be less intense. So let's say that I took an X-ray with an 8-inch PID, and then I changed to a 16-inch PID, but the doctor wants the all of the image to appear the same. We want the same density. We want the same contrast. So in order to maintain that, I've got to increase either MA or time because it's traveling farther. It needs more driving force now to be as intense. Hopefully that makes some sense. You can also use the inverse square law in a reference to, like I stated before, as the radiographer. So if I'm a radiographer, like I said, and I'm standing at 3 feet and I want to reduce exposure to me now, I need to move farther away from that source of X-ray. And I'm going to double my distance, which means that's going to decrease my exposure to 1/4 of what it was at 3 feet. So I'm going to 6 feet, so it's reducing my exposure by 1/4. It's 1/4 as intense. So hopefully that makes sense. I know the inverse square law can be kind of confusing. On the module, I put a mass problem and an inverse square law. So you guys can look at that and kind of use that little worksheet for practice. Mass is what I was talking to you about, where it's MA times time equals mass. And there a lot of times they'll ask questions like, if I increase my MA from 5 to 6 and my original, let's see, if I increase MA from, let's go 2 to 4, and what would my time need to be to maintain the same density as it was at 2? So basically it's one of those problems where you have to think about that inverse relationship between MA and time in order to maintain density. If my MA goes up, you know your time has to go down to end up with the same answer, the same density. So let's say my density is 8, my MA is 2. My time had to be 4 in order to have an MA, or to have a mass of 8. This is so hard to do without a board to write this on for you guys. Now if I increase my MA to 4 and I want to maintain that 8, now my seconds or my time need to decrease to 2. So hopefully that helps. There's that little worksheet if you want to print that out or look at that and write it out yourself, and kind of get in your head the inverse square law. You'll want to know the name of the inverse square law and basically kind of how that formula works. The inverse square law is the original intensity. Excuse me. So it's intensity 1 over the new intensity. A lot of times the new intensity is what you're solving for. So if that's the case, that would be whatever the original intensity was over x equals the new distance squared over the original distance squared. And then you do the algebra, the cross multiplication. When we're in lab together, I will go over this with you guys, and we'll do some of these problems so that you can actually see this in person. So don't worry about it. Like I said, there's that little worksheet that I have on the module if you want to play around with it. The last thing that they discuss in this chapter is the half value layer. When we were talking about the tube head and everything that's placed within the tube, remember we talked about the aluminum filters and how aluminum allows some of the X-rays through, whereas lead allows none through. So the aluminum filters are placed actually inside the tube head in the path of the beam, and they are going to remove those low energy, less penetrable, long wavelength X-rays that only contribute to scatter. So we want to reduce those, and we want to have a really nice, strong, penetrable beam. Think of like survival of the fittest. We want the strongest ones to make it through. Excuse me. The half value layer that they speak of is a thickness of specified material that can reduce the X-ray intensity by half. So it's exactly what it says. And aluminum filters are what are used in the X-ray tube. So basically that's all we're looking at, is what can I place inside the tube to reduce the intensity of that X-ray beam by half, and that in this case is aluminum. So I believe that is all for this chapter, you guys. I know you're going to have questions. This is the most technical chapter. I always slow it way down on this. Like I said, when I meet with you guys next week on Monday and Wednesday, we can cover like the inverse square law and any questions that you guys may have. And I hope you have a great weekend. Thank you.